Good morning. Today we'll be discussing wave-particle duality in quantum physics. After today's unit, you will be able to describe what wave-particle duality is in your own words and to determine when a quantum object behaves like a wave or a particle. So let's begin. So let me remind you that interference is a common wave phenomenon. And here is a clip of that. You have start with a wave, in this case a water wave going through two slits. After that, they start to interfere and create a pattern of bright, dark pattern on a screen. You may also wonder if we do this on particles such as sand, if I blow sands through the same double slit, what would happen on the screen? I think it just takes no time for you to answer this question, that you will see pattern like this. You will see two blobs, each corresponding to the sand going through each slit, right? And if the slits are close enough, the two blobs merge in one really big blob. So this demonstrates that classical particles do not show interference, do not exhibit any wave feature. However, in quantum world, a quantum object can exhibit properties that are both of wave and particle. This is the so-called wave-particle duality. So let me give you an example. If we use light that goes through double slit, and we see this interference fringes, this can be explained by wave picture, because the wave coming from here and there, they have different phases and they can interfere constructively or destructively, showing this bright, dark pattern. This happens even for very faint light, almost on average, not so much light going through, or in terms of language of photons, there may be just one or two photons going through at the same time. However, light can also display particle property in the same experiment. If we try to detect which slit the light goes through, if we use some detector, if light goes through and the detector will record that the light either goes here or there. If you repeat the same experiment with these detectors on, and you record the pattern at the screen, you see that the pattern on the screen looks exactly like blowing sand through the two slits. So in this case, the light, supposedly wave, lose their wave property and exhibit particle property. Another example is the electrons, and we all know electrons are particles. What if we shoot electron through double slit and collect the image at the screen? So let me give you some time for you to think about whether it's A or B, whether you have interference fringes or you just see one big blob. I'm sure you now all have the answer in your mind, and this answer can be revealed by experiment. As I play you the clip, the experiment was done by collecting electrons going through the slit one by one, recording the occurrence of electrons. The bright spots are where electrons end up on the screen. And if you keep collecting it, it looks like random pattern, but the more you collect, there is some pattern emerges. If we fast forward this, you see that at the end, it shows the exact bright dark pattern as in the interference fringes. So this shows that electrons actually exhibit a wave property, even though they are known as particle. So the next question that we will discuss is, how do we determine whether a quantum object will display particle or wave property? This actually depends on the so-called which information, whether the object goes through this path or that path. This is the so-called which way information. If this information is not known or cannot be known in principle, then it will exhibit a wave property, such as the light go through here without knowing which slit it goes through. For the example that you put a detector to see which slit the object go through, then it would not show any interference. The idea is basically there's only one path. If you know it goes through here, there's no way you can interfere. As for example, here there are two paths, so therefore you can interfere. This is how you determine whether it's particle-like or wave-like. And here is a self-check. So I show there is an experimental setup. There is a light source coming through a beam splitter. The light split and goes through a mirror, bounce back, and this other branch of light also bounce back to mirror, and they collect at this detector. This is what you see when you use a laser, and you see these circular interference pattern. This setup is actually used in this LIGO experiment that detect the gravitational wave. And this is the so-called Michelson interferometer. So you see fringes because light interfere from two different paths. So the question for you to check, the first one is, can you draw the two different paths that the light travels from source to the detector, the path that they interfere? B, if you move this object to block out one path, do you still see fringes, and why or why not? Do you think this is a quantum or classical phenomenon? Please post your answers in the discussion board and comment on at least one other person's answer. So that's the end of today's unit. There is further information showing further video clip that you can also watch, and this information will also be posted on the Blackboard. So I hope you understand what we have learned today about wave-particle duality and how to determine whether you will see wave or particle feature. That's it. Have a good day.